Okay, I think we'll go ahead and get started. We're recording it so we can our parents can see it. This is the Mawet Group. Take it away.
Hi, I'm Serina Jain,
And I'm Aayan Maheshwari.
and we're part of the Mawet Lab this summer as volunteer interns, not part of the SRC program.
So before we get started with the presentation, I'm going to go over a brief overview of what we will be talking about. First, we're going to be talking about what the lab does and like its purpose, and then we're going to talk about our project and the problem statement, why we are interning here. Then we're going to talk about implementation of the project, and finally, we're going to talk about some solutions.
Okay, so we're going to start out with the lab's purpose, which is detecting exoplanets using the direct imaging technique. So to start out, what is an exoplanet? An exoplanet is short for extrasolar planet, and the term refers to any planet outside of our solar system or not orbiting our sun. So as you can see with the image on the right, this is an exoplanet, an artistic representation, and in the foreground we see the planet, and in the background we see the star that it's orbiting.
So before we get started with explaining what the lab does, we're going to go over some key terms that might be helpful to know. The first is wavefront control. So a wavefront can be described as a function representing the light coming from the star. So we have the light coming from the star, but in that process of it traveling millions of light years, it can get distorted and lots of other things can happen. Additionally, there might be some issues in the optics in your system, which may cause distortions in your image. So we can use wavefront control to sort of compensate for that and get a clearer image. An example of this is adaptive optics. Adaptive optics is the use of some wavefront control techniques to compensate for the distortion you get in the atmosphere. So while the light from the star is traveling through the atmosphere, a lot more distortion happens than the process of the light going through the vacuum of space because of the millions of particles that it has to go through, and we get a really distorted image. And a really good way we can compensate for this, and it's widely used, is by using a deformable mirror. This deformable mirror is a use of a flexible mirror with a lot of actuators, and it bends in a shape such that it distorts the image in a way so that it returns back to its original shape, so we get an undistorted image.
Okay, so our next term is coronography. So as you can see here, this means the process of blocking out direct starlight to see nearby objects. So you might be familiar with the term corona, and this refers to the outer light of the sun that we can see. And so a fun fact is that centuries ago, the only way to ever observe the corona or solar flares was by seeing a solar eclipse where the moon would be blocking that starlight. But nowadays we can use coronography as a technique to block the starlight without having a solar eclipse. And then another way to think about coronography is if you have a fly next to a really bright light. And so the fly is going to be overshadowed by the light because it's so bright. But if you put your hand up to the light and block the light, you'll be able to see the fly. And so think about that, but on a much larger scale, where if the fly is an exoplanet and the bright light would be the sun or the star that it's orbiting, and that star is 10 billion times bigger. So it's much harder to do. And that's why with the Mawet Lab, it's really important we do high contrast imaging because it's so precise and the numbers are so big. And then our last key term is spectroscopy. So as you can see, it's measuring spectra to gain insight on atmospheric composition. And so what it does is that we look at the spectral lines, and that tells us about the different elements that are present in the atmosphere of whatever we might be looking at. And that can give us insight as to if that planet might be habitable for life. Okay, so now we're going to overview some exoplanet detection methods, so 3 to be exact. But the first one is the transit method, and the way this works is we're observing a dip in when the planet passes in front of the star or when it transits. So as you can see with the image here, we have a planet transiting across the star, and there's a drop in the light or a dip in the light when the planet passes by because it creates it makes the light of the star appear dimmer to us because it's blocking some of it. So that would be the transit technique. And then
another technique that's used for detecting exoplanets is the radial velocity method. This uses the fact that we all know that the star has a gravitational pull on the planet, but the planet also has a gravitational pull on the star, and it causes the star to wobble a little bit. As you can see in this graphic, you see the star is orbiting slightly, not around anything, but just around itself. And what we can see is that the planet, relative to us, the star is moving away and towards us. And we can use something called the Doppler shift. Doppler shift is a method of observing the light from the star and seeing whether it's moving away or towards us. So while it's moving away from us, the light appears to get redder and redder as the wavelength is being stretched. And then while it's moving towards us, it becomes bluer as it's being compressed. So we can analyze this by seeing the amount of shift in the light, by seeing how much the star is moving forward and backwards. We can analyze the size of or the mass of the planets. So these two methods are both indirect imaging techniques. So what this means is it allows us to indirectly infer some components of the planets that are orbiting it, such as its mass or size. But there are some other techniques for detecting exoplanets.
Yeah, so unlike the first two techniques we just mentioned, the third technique, called direct imaging, is a direct technique of imaging exoplanets, hence the name. And so the way that this works is we're actually observing the planet itself by blocking the starlight using coronagraphy and analyzing the composition using spectroscopy. And the reason direct imaging is special is because we're looking at the planet itself rather than by other means to detect its presence. So this actually is a technique used by the Mawet lab, and so we're going to talk a little bit more about this throughout the presentation. So to start out with the simplified direct imaging process, so the unique benefits of the technique. So kind of like what I already mentioned, because we're directly imaging the planets and spectroscopy is being used to analyze the atmosphere and the composition, this actually gives us a hint as to the habitability of the planet. So we can actually use this method to detect life, potentially, whereas other methods might not be as useful for that.
So then here's a brief diagram of what a coronagraphy setup would look like. So we have our sunlight or starlight coming from the source or whatever we're trying to observe. It goes through a couple lenses or other optics. Then it's focused on at a certain point or plane. And then at this focal plane, we actually place our coronagraph. This coronagraph is manufactured with extreme precision, this one being at the micron scale. So with this really extreme precision, we get such small artifacts, and we're able to use some techniques in quantum physics that allows to make the starlight cancel itself out while it's going through. Since, as you see, it's not a simple shade, but there's a really complex structure. So while the light is going through this coronagraph, it's being canceled out. So once it goes through the coronagraph, we can also have other things in between, such as the deformable mirror. As I talked about earlier, we have our incident wavefront with the light coming from our source. It goes to this deformable mirror, which is deformed using some computational techniques. And then we get our reflective wavefront, which allows us to see a more clear and less image with less distortion. And additionally, this deformable mirror can allow us to focus the light slightly better on our coronagraph. Since this coronagraph is manufactured at such a small scale, precision is required for where the starlight is hitting the coronagraph. And we can bend this mirror in such a way so that we can get the starlight focused on the coronagraph. And then I'll show you some examples of these techniques used in the real world. So we first have an image of a planet system with no advanced optics correction. So you can see there's lots of distortion and noise coming in the image. Then once we're able to apply our advanced optics or our deformable mirrors techniques, we get a lot less distortion, and you can sort of start to make out some features in the image, but it's still clouded by the amount of starlight in there, and you can't really see anything around the star. Then once we apply the coronagraphy technique, we can start to form a better understanding of what is around the star. So we can start to see the formation of a planet nearby. And then finally, we can also apply lots of post-processing techniques and a lot of other algorithms that allow us to see the star, the planet next to the star, and determine its mass or its orbit around the star.
So we wanted to show you a real-world example of what that might look like. So we're going to use the HR 8799 planetary system. You can see the simulation right here. This was actually captured by one of the Keck ground-based telescopes. And as you can see, the date range it was taken over a really long period of time. So it starts around 2009 and goes around to 2015. And we can see the planets are orbiting in the simulated image right here. And the star, if you notice, is black in the middle. And that's because all of the different advanced optics techniques, adaptive optics techniques that Aayan just mentioned are being used. So coronagraphy would be one of them. So that's the reason it appears to be black. And then scientists actually strive to have 10 to the negative 10 of the starlight being canceled out. So that would be the factor of the starlight being canceled out. So that's a really small number, and it's very precise. That's why we need to use advanced optics. And
so now we're going to talk about a little bit about the significance of the project and why we are actually doing this.
So to start out with the project's purpose, So first of all, we are just, the idea of our project is that we are building a new environmental sensing system for the high contrast spectroscopy test bed. So to start, what is that? What is HCST? Well, HCST is the test bed in our lab, in the exoplanet lab in Cahill. And it has lots of sensitive equipment for conducting experiments. And then what is environmental sensing? Environmental sensing is using sensors to detect the environmental factors that are the most important. So temperature, humidity, and pressure would be the main ones that we're focusing on. And we're doing environmental sensing within our test bed.
So now why is this type of environmental sensing needed? Like, why would the researchers care what the temperature inside the test bed is? So a really important fact is the deformable mirror, as I talked about earlier. The single deformable mirror used in the lab is worth about $1 million, which we probably don't want to have it get damaged. And it's extremely sensitive to humidity in the environment. So if it's running while the humidity goes too high, that could damage it quite severely, and it might be wasted. So we could set up a system with environmental sensing that allows the researchers to determine whether or not the humidity goes too high while they're running their experiment, and if it does, stop it in the process. Additionally, a lot of the optics are really sensitive to things such as temperature, because it can cause them to warp and cause inconclusive results in any of the experiments that they run. Additionally, in the past, there has been a setup for environmental sensing, but it was a really complicated system. And after a SURF student set it up and left, it didn't work as well as expected. And the researchers weren't able to figure out the solution to fixing the system and getting it working again. So this year, we decided to build a simpler system that is able to be troubleshooted really easily. And then here's an image of the deformable mirror used in the lab.
So now we're going to talk a little bit about how our project helps the Mawet lab. So we're going to go through kind of how environmental sensing impacts testbed experiments, and then how testbed experiments impact direct imaging, which is the large scale method that we talked about in the beginning. So to start with the latter, direct imaging depends on testbed experiments, as they act as a simulated or smaller scale version of what would happen for real. So we can anticipate any flaws. We can test out the instrumentation in a way that's a little bit more low stakes. And then the reason that the testbed experiments depend on environmental sensing is because since the equipment is so sensitive and it requires so many special conditions and environmental factors, we need to make sure that we can be able to sense this information. So environmental sensing gives us the machinery to be able to understand different factors about our environment, and that can inform our experiments.
Now I'll give you a brief overview of how we implemented our environmental sensing system. So a lot of it starts with this microcontroller. Many of you may know of what an Arduino is. This is very similar, but it's called an ESP32 and has Wi-Fi capabilities as well. So this ESP32 is connected to our sensor, the BME680. This is a very versatile and very useful sensor. On the single chip, it's able to detect temperature, humidity, pressure, gas composition, dew point, and altitude. Although some of these we may not need in our testing, it was a very versatile chip, and it's in a small package, which is why we decided to use it. So this ESP32 is connected to another database called UBDOTS, which is hosted by a commercial platform and allows you to really easily visualize the data. So right now, this is an image from a time when we had two sensors connected, and you can see how it's anybody can view this data and understand what's happening with different sensing in the lab. But again, since it's a commercial company, there were a couple of drawbacks. The main one being that without paying upwards of $100 per month on this platform, we wouldn't be able to store our data for more than a month or have readings any more often than a minute per sensor. So this is why we decided to use a secondary database, the Firebase real-time database. So with this database, we can upload every 5 seconds and have it for long-term storage for the researchers. But once again, we decided that there are a couple other drawbacks with this system. The main of such being that we can only store data for about 65 days before we run out with the amount of data that we're storing. So which is why we connected to another computer, SAM. SAM is a computer running locally in the lab, and it takes every 24 hours, it takes the data from Firebase, stores it locally, and then deletes it from Firebase to prevent us from going over any data limits. Then finally, SAM hosts a website for any of the researchers or any of the users of this platform to access, and allows them to quickly and easily download the data. It's a website that we made. It's not as nice as UBDOTS, but it works for the researcher's purpose. So yeah, that's a brief overview of our system and what we did. Now we're going to talk about some conclusions, what we learned, and what we will do in the future.
Yes, so we're going to talk about 4 of the main problems that we solved throughout the course of our project. So to start, we made the lab condition information readily accessible from outside the lab. So what this means is we now have the UV system and the fire-based system where we have remote sensing. So anybody who is anywhere in the world on any device at any time can access the data and it will be live data. So that was a huge accomplishment that we had. The second would be that the data is now much more easily stored and can be analyzed in the future to compare against tests. So prior to our project, data was being stored on a SIM card in an Arduino, which is much more difficult and it can't be uploaded every day. You can't really see the live data in the same way. So now we have 80 years worth of storage on SAM, which is the computer Aayan mentioned, and we can now use that and look at it at any place. So the third goal that we had that we accomplished would be that we set up an easy SMS alert system. So the reason that that was important is because researchers want to know if there's anything going wrong with the testbed experiments, if the conditions are not how they should be. So a good example of that would be humidity. It can't go above a certain threshold. So we want to make sure that it stays in a certain range. And so if there is a problem, this SMS alert system where it'll send a researcher a text if they need to know that the data is not how it should be, they can go in and fix that problem and anticipate it. Whereas otherwise it might be too late and the expensive machinery could be broken. And then to talk about our last problem that we solved, that would be we created well-documented procedures. So like Aayan alluded to, previously it was much more difficult with the SURF intern to kind of understand how the system was built and what exactly went into making it. And so we created well-documented procedures so that anyone who comes in the future will be able to fix any problems that occur because we have everything written down and they can understand our process really well. And so the image that we have right here, this shows the UV dashboard, only the special thing about this is it's projected on a TV in the lounge in our lab. So anybody passing by can see our live time data and they can see it in a nice comprehensible way. So that would be the main 4 problems that we solved throughout the course of our project.
And then another thing to note is that since we are not SRC students, we are here for another week and we have a couple of other things that we'd like to accomplish. The first being that we'd like to 3D print cases for all of our Wi-Fi modules and sensors. This is so that right now they are just a couple wires connected to a Wi-Fi module, and it's probably not the most secure setup. So we're going to 3D print some cases and have it so it's a modular setup and can be moved around anywhere else we would need. Additionally, we also like to add 2 new sensors, first being a vibration sensor. The vibration sensor is very useful, not necessarily for real-time data validation, but more so for analyzing the results that you get from the tests with some of this vibration data. So any issues that are caused by this, by the tests or anything that we don't get perfectly in our tests, we can see that in this vibration sensing data that there might have been like another unnecessary force in the environment and we might not have gotten a perfect reading from our sensors. So pretty much to summarize that, like anything like a car driving above the road would cause an issue which would affect our testing. Additionally, we'd like to add a light sensor. And what this light sensor is doing is pretty much detecting if somebody's in the lab or not. Since we have a policy set up so that anybody in the lab, if you're the first person in there, you turn on the lights. If you're the last person to leave, you turn off the lights. So this will give us a really quick understanding of whether somebody's in the lab or not at any given time to let the researchers easily know when to start their experiments. And then here's a couple sources that we use for some of our graphics throughout the presentation. Thank you. And
yeah, thank you so much. We really appreciate the opportunity to present, and it was great to hear everybody's amazing research.
do you have any questions?
Very impressive. And you're doing something they're actually going to carry through and use.
So you did a lot of hands-on things with pieces of equipment, and at the end you had to write up some documentation. Did you enjoy that last step?
Not as much as working with the equipment.
Yeah, that's usually the case in the brain, but it's a requirement for a lot of projects.
Yeah, we're actually still in that phase a little bit, so we're definitely continuing the documentation, and we're actually learning some things about our project on the way, and like it's kind of good to like help us realize too what the most efficient methods are as we're writing it down. So, any other questions?
Thank you. Thank you all.